Hello and welcome to Data Science for Everyone. Today we are going to take a deep dive on Matplotlib, a graphing library in Python. And by the end of this video, you'll become an expert on using Matplotlib. Let's get started. We'll start with the basics of Matplotlib and how to use it with respect to an object-oriented approach. We'll look how to visualize quantitative and statistical plots, time series plots, how to write functions, and finally we'll end with how to customize, export, and share plots. Let's start with the basics of Matplotlib. For this demonstration, we'll be using the sales dataset that contains the revenue for 4 different products in different regions of the world. We'll load the dataset using the pandas read CSV function and store it in the sales variable. There are several ways to use Matplotlib, but in this video we'll focus on an object-oriented approach. This method is accessed through the pyplot submodule. We start by importing this module and giving it the name plot or PLT. While naming it PLT isn't required for the code to work, it's a widely used convention. When we call the plot.subplots function without any arguments, it returns 2 objects, a figure and an axis. The figure is like the overall page. It holds everything you see in the final output. The axis is a specific area where the data is drawn. Think of it as the canvas where we'll create our visualizations. Then we'll call the plot.show function to display the plot. Right now, you're looking at a figure with empty axis. No data has been added yet. Now let's add some data to our figure. We'll subset product A using Boolean subsetting and store it in a variable called A. Then we'll add the month column as x-axis, which is the first argument, and the revenue USD column as y-axis as the second argument. Calling plot.show displays the line plot. Let's add the revenue for product B to the existing plot. To do this, we subset product B and call a second ax.plot function to add the revenues for product B. Notice that Matplotlib automatically adds different colors to each product. The plot method also accepts an optional keyword argument called marker. This lets you add markers to your plot to highlight individual data points. For example, if you pass the lowercase letter o as the value for marker, it tells Matplotlib to use circles as markers. This is a simple way to make your plots more visually informative and easier to read. If you use the lowercase letter x instead, the marker will appear as crosses instead of circles. To explore all the different marker styles, you can check out the official Matplotlib documentation online. You can take things a step further by changing the appearance of the lines that connect your data points. This is done by using the line style keyword argument. For example, if you set the line style to dash dash, the line will appear dashed instead of solid. Just like the marker shapes, there are several line styles you can choose from. You can find the full list in the Matplotlib documentation online. By customizing both markers and line styles, you can make it even clearer that lines are just connectors between individual data points. The line can be removed as well by simply setting the line type argument to none. You can choose to color the plot by setting the color argument. Here we set the color argument to G to show the data in green. Another important aspect of creating effective visualizations is labeling your axes. If you want your plots to communicate clearly, you should always label the axis. It's a small step that's often overlooked but makes a huge difference. The axis object provides several methods that begin with the word set, which you can use to customize different properties before displaying the plot. For example, you can use set_xLabel method to set the label for x-axis. When writing axis labels, follow the standard sentence capitalization. Capitalize only the first word unless there are proper nouns. Once you have set the label, calling plot.show will display the plot with updated x-axis and y-axis labels. Similarly, the plot title can be added by calling the setTitle method. In some cases, adding more data to a plot can make the plot too busy, obscuring patterns rather than revealing them. Therefore, it's better to split the plots into small multiple plots to make the visualization more effective and clutter-free. In Matplotlib, Small multiples are referred to as subplots. That's why the function used to create them is called subplots. Earlier, we used this function without any arguments, which gave us just one subplot. Now we'll pass some arguments to create multiple subplots. Small multiples are usually arranged in a grid of rows and columns. In this example, we are creating a figure with 2 rows and 2 columns of subplots. Before we add any data, this is what the layout looks like. Notice that in this case, the variable x or ax is no longer a single axis object. It's now a 2D array of axes, one for each subplot in the grid. To add data to a specific subplot, we'll need to index into this 2x2 subplot array and then call the individual plot method on the individual axis that you want to use. This gives us full control over each subplot, allowing us to customize and populate them individually. In this example, we index the top left subplot with 0, 0 and add the A revenue data to it. By setting a different index, we can display another set of data to the subplots. Here we index the top right subplot using the index 0, 1. Here is the full plot that displays the revenue for each product in different colors. There's a special case to keep in mind when you have only one row or one column of subplots. In these situations, the array of axis objects becomes one-dimensional, so you will only need a single index to access each subplot. Let's take an example. We create a figure with 2 rows and 1 column of subplots. This gives us a vertical stack of 2 plots. We access the first element in the array, this is the top subplot, and plot the product A revenue. Then we access the second element, the bottom subplot, and plot the product B revenue. We can also add y-axis label to each subplot to describe the data. Since the plots are stacked vertically, we can only add one x-axis label to the bottom plot by setting it on the second element in the array. When we display the figure, each subplot is clearly labeled and easy to interpret. One more thing we need to address is the range of y-axis in our 2 subplots. By default, each subplot sets its y-axis range based on its own data. But if the highest and the lowest values differ between datasets, as they often do, the y-axis won't match. This can make comparisons harder. To fix, we can initialize the figure and subplots with the keyword argument share y equal to true. This tells Matplotlib to use the same y-axis range for all subplots based on the combined range of both datasets. Now the comparison between the 2 datasets become much clearer and more accurate. We move on to the next segment where we will see how to create quantitative and statistical visualizations using Matplotlib. A quick detour before I move on. Looking at the YouTube data, I can see that only 9.3% of you have subscribed. If you have enjoyed the video and learned something new, please consider liking this video and subscribing. Let's bring in the penguins dataset using the pandas read CSV function. We clean up the data by removing any NAs that might interfere with plotting. The dataset contains information about 3 different species of penguins, which we'll be using to create visualizations. By the way, all these data are linked in the description below. Let's say we want to know how many different individuals are there for each penguin species in the dataset. We first need to do some calculations to count the penguins for each species. We group the penguins data frame by both species and sex, count the number of entries in each group, and then reshape the result into a table with sex as columns, filling in the missing values with 0. So in the end, you will get a clear table showing how many male and female penguin belong to each species. Now let's make a bar plot using the penguins count data for the male penguins. We'll start by creating a figure and axis object, and then use the axis bar method to make the bar chart. Each bar in the chart represents a row from the species column in the dataset. The height of each bar shows the number of male penguins for each species. We can rotate the x-axis tick labels by 90 degrees by using the set_x tick labels method of the axis object by selecting the index column and setting the rotation argument to 90 degrees. Next, let's add the data for the female penguins. To include all this information in the same bar chart, we'll create a stacked bar chart. In a stacked bar chart, each new set of data is stacked on top of the previous one. We'll start just like before by plotting the male penguins. Then we make another call to the bar method and add the female counts. This time we use the bottom keyword argument to tell Matplotlib to stack the female counts on top of the male counts. Finally, we rotate the x-axis labels by 90 degrees, set the y-axis label, and call plot.show to display the chart. To make the chart easier to read and understand, we also want to show which color represent each penguin's sexes. To do that, we need to make two changes. First, we need to set the label argument to either male or female, and second, call the axis.legend method. This will add a legend, as we can see on the top right of the plot. Bar charts are great for showing the value of a variable across different categories. Histograms, on the other hand, are useful for showing the distribution of values within a single variable. Instead of comparing categories, a histogram shows how different values are spread out. Let's take a look. We subset each species of penguins into different variables. Then we create a figure and axis object just like before. We then use the axis hist method to plot the entire body mass column for each penguin species. In the resulting histogram, the x-axis shows the range of body mass values, and the height of each bar shows how many penguins fall into that range, or bin. Each species has a different color as well. You might be wondering how Matplotlib decides how to split the data into bars in a histogram. By default, it uses 10 bins, which means it divides the range of values into 10 equal parts. But we can customize this. If we want more or fewer bars, we can simply pass an integer to the bins keyword argument. For example, setting bins equals to 30 will divide the data into 30 bars, giving us more detailed view of the distribution. Sometimes part of a histogram can be hidden behind other bars. This is called occlusion. We can fix that by changing the type of histogram we use. Instead of the default bar type, we can set the hist type argument to step. This draws the histogram as thin outlines instead of solid bars, making it easier to see overlapping data. We learned how to create histograms to compare data distributions. But how can we display more information? That's where statistical plotting comes in. It's a set of visualization techniques designed to help us compare data more precisely and clearly. Let's explore two of these techniques and see how they can reveal patterns and differences that might not be obvious from basic plots. The first technique is using error bars in plots. Error bars are extra markers on a chart that give us insight into the spread or variability of the data. While histograms show the full distributions, error bars summarize that distribution using a single number, like the standard deviation. Let's add error bars to the bar chart. Each call to x.bar method takes two arguments, x and y. X defines the species and y defines the mean body mass of the penguins. We then use the y-er or yerr keyword argument to set the error bar. To this argument, we pass in the standard deviation of the body mass column, which is shown as a vertical line on top of the bar. We can also look at the change in body mass for each species of penguin over time. First, we calculate the mean and standard deviation of the body mass for each species and store them in separate variables. Then, we call the plot.errorbars method with the x-axis set to year, y-axis set to the mean of the body mass, and yerr set to the standard deviation. We add the legend and call the plot.show method to display the plot. The second statistical visualization technique we'll explore is called the boxplot. Boxplots are available as a method of the axis object in Matplotlib. To create one, we'll pass in a sequence of sequences. In this case, we create 3 data frames, each for each species of penguins, and pass those data frames to the boxplot method as a list. Since the boxplot doesn't automatically know the labels for each dataset, we have to add them manually. We do that by using the set_x tick labels method. We also label the y-axis. Finally, we display the figure. This type of plot shows several key features for each distribution. The orange line in the center marks the median height. The edges of the box represent the interquartile range from 25th to the 75th percentile. The whiskers extend to 1.5 times the interquartile range beyond the box. If the data is normally distributed, this should cover about 99% of the values. Any points beyond the whiskers are called outliers, which are the unusually high or low values. For example, in this plot, we can see 2 points that are unusually long and short chinstrap penguins. Bar charts are great for showing the values of one variable across different categories, like comparing body mass of each penguin species. But what if we want to compare two variables across observations? This is called bivariate comparison, and a common way to visualize it is with scatter plot. Let's look at an example using the penguin dataset we have worked with before. The dataset includes measurements of flipper lengths and body mass for the penguins. Since these measurements are paired, we can represent each pair as a point on a scatter plot. The x-axis shows the body mass measurement, and the y-axis shows the corresponding flipper length measurements. To create this plot, we start by initializing a figure and the axis object. Then we call the scatter method on the axis, passing in the two columns. The first argument sets the body mass along the x-axis, and the second sets the flipper length along the y-axis. We also label both the axes, so it's clear what each one represents. And finally, we call the plot.show method to display the figure. We can customize scatter plots just like we did with other types of plots. Let's say we want to compare all three species of penguins side by side. To make the comparisons easy to see, we'll use different colors for each species. First, we filter our data to create 3 separate data frames using pandas. Next, we'll plot these data sets on the same scatter plot. We start with the Adélie penguins and label it as Adélie. Similarly, we add and label the 2 remaining penguin species. To help viewers understand the colors, we add a legend. We also include the axis labels to show what each axis represents. Finally, we display the plot using the plot.show method. When we look at the final figure, we can see that the Gen 2 penguins have larger flipper lengths and body mass compared to Adélie and chinstrap penguins. This example shows how using color can make comparisons in the data much clearer. We can also use color to represent a third variable in a scatter plot, which adds even more information to our visualization. In our penguins dataset, the bill length is stored as a continuous variable. We can use this bill length information to color the points in the scatter plot. To do this, we pass the bill length to the C argument, short for color, in the plotting function. Note, this is different from the color argument we used earlier to set a fixed color like red or blue. The C argument lets us use a variable to determine the color of each point. As before, we add axis labels and call plot.show to display the plot. In the resulting figure, the color of each point reflects the bill length of that measurement. Dark blue points represent penguins with shorter bill lengths. Bright yellow points represent penguins with longer bill lengths. This technique helps us see how the data changes for each individual observations, all within a single plot. Now let's add a regression line to the scatter plot. This is a bit more advanced as we need to compute the regression line. First, we make the scatter plot as usual. Then we compute the regression line. We use numpy's polyfit function to perform a linear regression between the penguin's body mass and flipper length, fitting a straight line to the data. The 1 indicates a first-degree polynomial, which is a straight line, and the function returns a slope and intercept of that line. These values can be used to predict the flipper length based on the body mass. Then we use the plot method with the penguin's body mass as the first argument and the regression line data as the second argument. We color the line red. Calling plot.show displays the plot. A lot of data is organized as time series, which means it's recorded over time. Visualizing these kind of data is a powerful way to spot patterns and trends. take the sales dataset, which we use to demonstrate line plots in the beginning of the video. It's a simple example of time series data. In it, continuous variables like revenue is organized by time, specifically by months of the year. In this part of the video, we'll go further and learn how to use Matplotlib to visualize time series data more effectively. Now let's look at a more complex dataset that tracks climate changes over the past 30 years. The data is stored in a CSV file with 3 columns. The first column, date, shows when each measurement was taken using the year, month, day format. A reading was recorded on the first day of almost every month from 1993 to 2025. The second column, ppm, contains the amount of carbon dioxide in the atmosphere measured in parts per million. The third column, relative_temp, shows the temperature on that date compared to a baseline, the average temperature during the first 10 years of the dataset. To work with this dataset as time series in pandas, we need to tell pandas to treat the date column as actual dates. One of the ways to do it is by calling the pd.toDateTime method on the date column. We also want to set the date column as the index of the data frame using the set_index function. This lets us take full advantage of pandas' powerful time-based indexing features. To start plotting the data, we first create a figure and axis. Then we plot the data using the data frame's index for the x-axis and the CO2 ppm column for the y-axis. We also add labels to both axes. Matplotlib automatically formats the x-axis to show time in 4-year intervals using years. The resulting visualization tells a compelling story. While there are small seasonal changes in CO2 levels, the overall trend is clear. CO2 in the atmosphere has steadily increased from around 320 to 430 parts per million. We can focus on a specific decade of data by slicing the data frame using 2 date strings, one for the start and one for the end of the period we're interested in. This gives us a plot showing just those years of the time series. Matplotlib automatically adjusts the x-axis, labeling it with years and placing ticks at 1-year intervals. Similarly, we can focus on a specific year of data by slicing the data frame using 2 date strings, one for the start and one for the end of the year we're interested in. As usual, Matplotlib automatically adjusts the x-axis, labeling it with months and placing ticks at 2-month intervals. Let's say we want to plot both carbon dioxide and relative temperature. Just like before, we create a figure and axis and then plot one variable, say carbon dioxide, on the graph. After that, we add a second variable, relative temperature, to the same plot. We also label the axis and display the plot. But something looks off. The carbon dioxide line appears to be shifted upward, while the temperature line looks almost flat. That's because these 2 variables are measured on very different scales. Carbon dioxide is in the hundreds, while relative temperature changes are much smaller. This difference in scale makes it hard to compare the 2 variables on the same axis. You have already seen how to plot time series in separate subplots. This time we'll plot them together in the same subplot, but with 2 different y-axis scales. We start by plotting the first variable, carbon dioxide, on the main axis, setting it as x1. Then we use the twin x method to create a second axis that shares the same x-axis but has its own y-axis. We call it x2. We plot the second variable, relative temperature, on this new x2 axis and display the figure. Now we have 2 y-axis scales, one on the left for CO2 and one on the right for temperature. You can now clearly see the temperature fluctuations, but there is still a problem. Both lines are the same color, which makes it harder to tell them apart. Let's fix that. To make it easier to tell the 2 variables apart, we'll use different colors for each one. We assign a color to the first variable, carbon dioxide, by using the color keyword in the plot function. We also set the same color for its y-axis label using the setYLabel method. Then we do the same for the second variable, relative temperature, on the twin axis. We choose a different color for both line and y-axis label. We have also colored the ticks for each axis as well using the tick params method and setting the desired colors using the label color argument. In the final plot, each variable has its own distinct color, and the y-axis labels clearly show which scale belongs to which variable. When working with data analysis or visualization in Python, you'll often find yourself repeating the same block of code. Instead of rewriting that code every time, we can define functions to package those steps into reusable, organized units. Functions make our code cleaner, easier to read, and more efficient. They allow us to avoid repetition, reduce errors, and make our programs more modular, so we can focus on the logic and not rewriting similar code over and over again. Let me demonstrate with the time series dataset. We use the def keyword to define a function called plot_time series. This function takes several inputs: an axis object to draw on, the x and y data to plot, a color to represent the data, and labels for both x and y axis. Inside the function, we use familiar axis methods: plot to draw the line, set x label and set y label to label the axis, and tick params to style the tick marks. Now let's see how the function works. We call this function, and as arguments we call the first axis as x1 and the CO2 data along with its corresponding blue color and ticks. We also call the function a second time with the relative temperature and its corresponding red color and ticks. Finally, when we call plot.show, we see that it plots the time series data without repeating any code. One way to highlight a specific part of the plot is by adding an annotation. This means placing text and an arrow that points to a particular data point, helping us explain what's happening there. For example, let's say we notice that the relative temperature first exceeded 1 degree C on May 6, 2020. We want to point that out in our plot. We start by generating the plot using the plot_time series function we defined earlier. Then we use the annotate method from the axis object. At a minimum, this method needs two things: the text to display, in this case a string called custom label, and the coordinates of the point we want to annotate. The x coordinate is the timestamp for May 6, 2020, and the y coordinate is 1, since that's the temperature value. But when we run this, the text overlaps with the axis tick labels, which doesn't look great. So we'll try moving the annotation to a better spot. The annotate method has an optional xy text argument, which lets us choose where the annotation text appears on the plot. After trying out a few positions, I found that placing the text at the x value of March 6, 2005 and a y value of 1.2 degrees works well. However, there's a problem. It is not obvious which data point the annotation refers to. To fix this, let's add an arrow that points from the text to the actual data point. To link the annotation text to the data point it's referring to, we can add an arrow. We do this by using the arrow props keyword argument, which stands for arrow properties. This argument takes a dictionary that defines how the arrow should look. If we pass an empty dictionary, the arrow will use the default style. We can also customize the arrow's appearance. For example, in this case, we set the arrow color to green. There are many more ways to customize the arrow, and you can explore these options in the Matplotlib online documentation. Now that we have an understanding of how to create different types of plot, let's look at how to export high-quality plots for use in presentations and publications. We can change the overall plot style by adding the plot.style.use method. There are several preset styles in the Matplotlib online documentation. The default style is called default. We can set the plot dimensions using the fig size argument in the figure method. The width and height can be set in inches. In this example, we set the width and height of 10 by 6 inches respectively. Finally, we can export the plot using the savefig method. Here's an example of how to export a high-quality plot using Matplotlib. The first argument is the name of the file that will be exported. DPI or dots per inch is to set the resolution. In this case, we set it to 300. File format is specified as PNG. but you can also use other formats like PDF, SVG, or EPS for vector graphics. That brings us to the end of the video of how to generate plots using Matplotlib. If you like this video, please subscribe to my channel. I plan to bring new videos every week. Also, please like the video if you have learned from it and comment on what else you want me to cover. Thank you and happy coding.